Okay, hi girls. These are some important concepts for combinations. We won't need everything that we do here today, but the course requires that we all look at it together, and some of it will really deeply inform how we move forward in the field of probability. So in this video I'm going to be looking at arrangement, both with and without order, factorial notation, choose notation, and a couple of sample questions. So, let's imagine we have these four individual unique elements, and I want to put them in order, maybe from first to last, or maybe I'm selecting them out of a hat, or maybe they're going to pass me through time. But so long as first, second, third, fourth, or written in a line, we understand that they are definitely in order. So how can I do that? Well, a common method is to start with one of the letters or one of the elements and put it first, and then choose another one. And so exactly as we've got there, YPGH. And then we might try again by putting Y first and P second, and then swapping around H and G. So they are unique orders. Now I've used up all the combinations that are possible, all the permutations possible starting with Y and P, so I'm going to have to go to Y and H maybe, YH and then PG, YH and GP. So I don't think I've messed that up. No, that's right. So we've had YP, we've had YH, and all the possible permutations of that. So let's have YG, YGHP, and YGPH. Now if you wanted to, we've used up now all the possible combinations where we start with Y, permutations, all the possible permutations where we start with Y and then have the letters following. We could then swap to the next letter and choose whatever and have P and do the same process again. And this would be fairly time consuming and not necessary because it's done for you. Okay, so here's all the possible permutations, and permutations means an ordered selection. Each one of these is unique because although the letters in each of them are the same, the order is different in each one of these. And I kept them so that we could see very clearly I started with a different letter each time, and we end up with 4 groups of 6. So the study of ordered selections is permutations. And unfortunately in this course, we're required to study combinations without really studying permutations by themselves, which is a little odd to me, but that is the course. We're acknowledging permutations, but we're just using them to move past them and get to combinations. So these are permutations, they're ordered selections. Okay, let's have a look at a slightly different way that we could have arrived at. How many did we have there in the end? Sorry, I don't think I said. We ended up having 4 groups of 6, or 24 possible permutations of those 4 elements, 4 people, 4 objects, whatever it is, in order. So, is there a quicker way of working that out? Yes, there is. We started by having 4 possible ways to choose our first letter or first object or first whatever. For each of those, there were 3 possible ways of going from there. So there were 4 possible starting points, and for each of those 4, there were 3 possible branchings from there because of the 3 leftover objects after each initial selection. Then on the ends of each of these is another 2, because there's 2 leftover objects to go after these. And then at the very end there's only 1 leftover object for each of those. And we end up with the same number of objects, and we could just say this is 4 by 3 by 2 by 1. Gives us the same answer. This is where we get this idea of factorial notation. I once got a question wrong in a very important test at university when I was training to be a mathematician, mathematics teacher. Because I was so excited about my answer, I put an exclamation mark on the end of my answer, and my lecturer gave me a big cross, but gave me full marks and said, oh, okay, well, you've either not seen or haven't remembered. An exclamation mark means you take the number and you multiply it by all the preceding numbers until you reach 1. Well, that was exciting. You'll find it on your calculator. Have a look for the number 4 factorial. Okay, you might want to pause the video and have a look for it. Hunt for, sorry, not 4 factorial. Hunt for the symbol, the exclamation mark. Once you've found it, try going 4 factorial and see if you get the number 24. Okay, moving right along. It can save a heck of a lot of time using using factorial on your calculator. Say I wanted to know how many different ways can I order 20 objects in a row from start to finish. How many different ways can that occur? It could be a horse race, could be 20 people arriving at a house, I don't know, it could be anything. We can just go 20 factorial, which is 20 times 19 times 18 times 17 times 16 all the way down to 1. I'm going to type that into my calculator. If you haven't found it yet, the button is below the on button. And we get 2.4329 times 10 to the 18. So working with probability means often working with very large numbers. If we were to write this number out in full, it would be a number that started with 2, and then we'd have to jump the decimal point 18 places. This would be a very, very large number. All right, moving along. Okay, so far we know how to choose. We know how to find out how many ways you can arrange a whole bunch of objects. But what if you've got a bunch of objects, but you only want to pull out a smaller number of objects and see how many ways those arrangements can be made? So if you had 5 objects and you only wanted to choose out 2, well, we have this lovely formula that is 5 factorial. That is our n. N is 5. But how many things do we want to choose? Well, let's call that R. We have this lovely formula that comes from the field we don't have to study in depth called permutations, and we would write 5p2, and what that does, let me give you the formula first. npr equals n factorial, which is our 5 factorial, on n minus r factorial. Now, I did say we don't study permutations, but we are having to go past permutations, to get to combinations, in which we do have to study. So, using the formula, we know our n is 5, so we go 5, and our r is 2. All right, and what this will do is go 5 times 4 times 3 times 2 times 1. Sorry, that's a 3. But underneath we get 5 minus 2 is 3. 3 factorial would be 3 times 2 times 1. So what happens is these cancel and leave with 5 times 4, which is 20. Now you can do that on your calculator quite quickly, but I want you to think about it for a moment. If we had 5 objects and we're only choosing 2, we started with 5 possible objects, and then we imagine that tree diagram again, 5 possible objects, 1, 2, 3, 4, 5, and of each of those 4 remaining objects, 4 possible things, 5 times 4. Okay. So that's permutations, and there's our formula there. Let's not rub it out. Yep, there's our formula there. NPR is when we have ordered selections. Now let's return to our Yancey, Phyllis, Graham and Hetta, or whoever they are, our 4 objects. If I want to choose 2 from here, I could go NPR equals n factorial on n minus r factorial. Or in this case, if I had 4 objects and I wanted to choose 2, then I'd have 4 factorial on 4 minus 2 factorial, which is 4 factorial on 2 factorial. And you can imagine 4, 3, 2, 1 divided by 2 times 1. The 2 and the 1 would cancel, leaving 4 times 3. So there are 12 ways we can select 2 objects in order from this group. 12 ways. Oop, too far. Let's have a look at them. YP, YH, YG. Those 3, those 3, and those 3. But now we get to move to combinations. You see, when they're in order, then HP, for instance, is unique to PH. But let's imagine these objects were people. And I had 4 people, and I wanted to invite 2 of them to go bowling with me. 2 of these 4 people. Then order would not be important. I wouldn't care, there would be no difference, between having Hetta and Phyllis and, where are they? Phyllis and Hetta. If it was an ordered selection, there would be a difference, but if it's unordered, we need to take these double ups and get rid of them. Oops, these double ups. See there, there's one. And in fact, you'll notice that they, in this case, pair up. So HG would have G somewhere, GH. Luckily, we have a shortcut for that too. We'll use the formula that we're mainly going to use in combinations, and that is N, that's an N, dear oh dear, that's terrible. How about I just draw it again? NCR. So it looks a lot like our permutations formula. Starts the same way. So it's n factorial on n minus r, but what's the difference is we need a way of cancelling out these double ups. These ones where we've got, that's not a double up. There's HP and PH. Oh yes, there's a double up, HP and PH, GH and HG. We get rid of those by putting r factorial down here as well. So in this case, what will happen, we've got 4 objects. We're choosing 2 of them. 4 factorial on 2 factorial. 4 minus 2 factorial. And that will give us 6. Okay. So what the heck is all that about? It's found our ordered selections and then has cancelled out all of the times where we get the same combination of elements and we don't care what order they're in. Essentially, this is the study of combinations, the unordered selection of a number of elements from a group of elements. This ugly formula here, NCR equals n factorial on r factorial outside of n minus r factorial. We don't have to use it. We have to explore it, we have to see where it comes from, but we don't have to use it. This is how how choose notation or combination notation might appear, either NCR or NR in a big bracket. Here's an example of the type of question you might have. I've got 13 objects, people, things in my fridge, doesn't matter. I want to choose out 3 of them, but I don't care what order they're in. So it's a C, not a P. And this is where we are for the duration of this part of the course, is combinations. Now again, I want you to have a look at your calculator, because your calculator has NCR on it. Instead of having to go 13 factorial on 5 factorial outside of 13 minus 5 factorial, we can just go 13C5 using our calculator. So type in the number 13, press Shift and divide. Yes, that's where it's hiding. Shift, then divide. And then, how many are we choosing? 5 objects. And there's 1,287 different combinations in which we can choose 5 objects from 13 objects. All right. Here's an example of a rather relatively complex application of combinations. There are 8 boys and 5 girls in the class. Ginny can only invite 3 boys and 3 girls to her party. Rude. How many different combinations of people could be at her party? Well, let's just deal with the boys first. She's got 8 boys and she can only choose 3. And that will be some number, which I'll just grab my calculator. 8, shift, divide 3. So there's 56 different ways she can choose 3 of the boys. That's a lot of combinations from the 8 boys. What about the girls? She's got 5. She can choose 3. So 5C3. 10. Now this is where it gets a little tricky, but we can solve it easily. What do these two numbers have in relation to each other? Well, each of these 56 represents one group of 3 boys. Each of these 10 represents one group of 3 girls. For every one group of boys, there's 10 possible ways you could get a group of girls. So to get the total number of combinations, we would need to multiply both of those outcomes together. Alright, lastly, have a look at this. I'd like you to grab your calculator, and using your calculator is good practice for application of combinations. I want you just to replace each of these little choose notations with a number by grabbing your calculator, in this case pressing 1, choose 1. And in this case the answer was 1, so I'm just replacing the choose notation with the value of the 1C1. If you go through and do all of them, you'll see something fun. Good luck with getting stuff done. There's a thing on MathSpace that I put up for you that relates directly to this, or if you'd like, there's an exercise uploaded onto Moodle from a lovely textbook, and good luck. Bye.